The following content has been provided by RWTH Aachen University.
All right, folks. Good morning, everybody. Thank you for coming to iOS application development. We are now at lecture 3, and we'll continue discussing the basics of Swift today and take a very first initial sort of glimpse at what UIKit looks like. So before we dive in, let me first give you a very brief recap of what we talked about last time. What you saw were some Swift basics, right? And I tried to draw out those things that, as a computer science student, you should be interested in knowing because they are sort of more timeless patterns or unique capabilities of this programming language that you can then use to compare it to others, right? So we did talk about the fact that Swift actually really likes constants, right? So as a Swift developer, you want to stick with constants as long as it's possible, and only if you really need a value to change later, you go to a variable. That's just, a programming, I would say, convention that makes for safer code and fewer bugs. Similarly, type inference is strong in Swift, so very often you'll see code that doesn't actually specify the type of a variable or a constant, but rather has it inferred from the initial value that's being assigned. And that is also something that is just, has established itself as a convention, makes for shorter code, and also lets the compiler decide, what kind of value or what kind of type you are looking for. Optionals are a big one in Swift. This is a pretty unique feature that lets you explicitly decide whether a variable should be able to not have a value or not, right? Whether it should be able to have this nil value that indicates that there is no reasonable value to assign to something. In other languages, this is always possible, and Swift makes it impossible by default to not have a variable. So to not have a value, and you need to explicitly define an optional and ensure that you deal with all the cases. And getting from optionals to non-optionals is a bit tricky. But we'll talk about this more because this is really one of the pitfalls if you do Swift programming and you don't understand this concept well. And then we talked about tuples, just a little nice modern feature that you can work with lots of things. You can even have the left-hand side of an assignment can be a tuple, which is maybe a little unusual if you're used to more traditional languages. Lots of more stuff. And after we wrapped that up, we went into the IDE and took a look at the basics of Xcode. But we also showed you some other ways of running Swift, right? You can actually open it up in the terminal. You can open the rapid evaluation print loop, the REPL, or you can launch a Swift playground inside Xcode. And to just try out some things, have like a scratch pad to try out a little bit of code, and you'll actually find that Swift playgrounds may seem even a bit reminiscent of Jupyter notebooks, where you'll find instruction materials and tutorials that have explanations and then a bit of code in there, all inside Swift playgrounds. And then of course there's the full-blown Xcode environment. By the way, if you have an iPad, you can actually run Swift playgrounds on there as well. So that's another way to get your daily fix of Swift coding if you don't have your laptop with you. Now, what we also covered was how you dig into Xcode a little deeper and actually get a project set up, how you do some project settings. Renee gave you a quick tour of how that works, how the emulator is being launched, or the simulator, I should say. And we took a very first look at how you tie together code and your UI, right? This is in technical HCI, which is sort of our research field. Whenever we look at a new environment, a new toolkit or a new language, this is one of the key challenges. How do I bind my code to the UI that I'm designing, usually graphically these days, right? And every environment does it differently. There are some patterns that are emerging. And the one that you saw yesterday, where you can basically graphically drag from your code to the UI and back to create connections between your interface and the code. That's one pattern that you'll see quite often in recent environments. There are other ways of doing it. Swift UI will show you quite a different way of actually handling that. Now, here's an extra one. This wasn't in the slides before, but I added this because I think it's really important for you to get if you are learning with us right now. Remember what we said about the textbook. This book, Developing in Swift Fundamentals, and there's another one on what's called data structures, I think. These are really useful to read along. So if there's anything in the class that you're not quite sure about, get these free ebooks from Apple Books. And they include the material on Swift that we talk about. They have more details on this. They take a slower pace. But actually, it's a reasonably quick read nevertheless. And what's also in there is tutorials on how to use Xcode Interface Builder and the documentation browser. And these are quite useful for you if you I know whenever I encounter a new IDE, the first thing is like, how on earth am I finding documentation, right? How am I getting help on what's the parameters for this call, et cetera, et cetera. And Renee gave you a tour of how to do this in Xcode, but these books have a little bit more information about this. Now, one caveat is these are on Xcode 13, right? So since these materials take quite some time to prepare, they're always lagging a little behind the latest version of Xcode itself. So this is Xcode 13, but the changes in beginning development are not that big, so you should be fine with most of the tutorial material that's in there. What's also useful inside these books is that there are actually interactive multiple choice tests. So the ebook has a page that has a test question, and it asks you to tick one or more answers, and you can check for yourself whether you're right or not. And if you're not, it'll tell you. And you can go back and reread the material to make sure that you understood it. In the beginning, these will be like super easy, right? You'll just breeze through them, but then after a while, you're like, oh yeah, I actually didn't quite remember what that definition of whatever structs or inheritance or optionals actually meant. So they are a really good way for you to check whether you were on top of the material. Also, just to indicate what I said initially, we are currently, at this point, about halfway through the fundamentals book already, right? So we're going fast, but as I said, the book is taking a slower pace, but it's also easy to read, so you should be fine. The other resource that we haven't mentioned yet, but I wanted to point it out, is that when you open these ebooks and you get to each new section, they will also have a link in pointing you to the Swift programming language book, the section that's relevant in the Swift programming language book about that topic. And what's that book? Well, this is the official authoritative source on how Swift works. It's the one that gets updated whenever a new version of Swift comes out, and it's kind of like this is going to be ultimately your Bible that you read, next to, of course, the built-in function per function documentation that you get when you use your documentation browser, right? But if you want a coherently written text that is authoritative on Swift, that's the book to go to, and that will also be very up to date. So it's currently on 5.7 already, and each time you see a new section in these fundamentals books, there is a link pointing you to that language guide, this language book. You can get it online there at swift.org. You can browse it there, or you can actually download it also as an ebook, as an EPUB, and put it on your iPad or on your computer and have it offline. So remember, these resources are out there. They're really useful, and they're now you have like 3 different ways of looking at the material, and that should give you a good idea of all of these concepts. Now let's go on. We're going to talk about strings. Strings are collections of characters. Surprise, surprise. But different than, for example, it used to be in C back in the days, where it was basically just ASCII characters or maybe 8-bit, but you had to add a 0 at the end to end a string. There were all kinds of weird hacks back in the days. Nowadays, strings are just Unicode collections of characters, right? So you can put anything you want in there, just as you could actually into variable names and things like that. And this first line, your second line, actually indicates something already. What you can see is that strings are not a simple data type, but they actually are something that you can call, maybe this looks like, it has a different component, right? It has a different property than just its actual contents. So string.count gives you back how long the string is. So you're not calling a function here, you're actually asking for a property, which indicates that strings seem to be some kind of struct or something, right? So there's obviously more going on here than we have. Now, what's also different about Swift from what you might be used to in other languages, especially C-based languages, is usually you have like strings, you use double quotes, right, for defining a string, and then you've got character as a different data type, and it's like a single quote thing, and you can clearly distinguish the two. Now, character also exists in Swift, and you can define a character. If you have an individual character, you can make that of type character, but single characters are most often actually strings in practical use. So that's why when you do define a single character literal like this, it will actually be typecast or type defined into, or type inferred, I should say, as a string, not a character. You need to say so explicitly that you want this to be one. Otherwise, it's a string, and letter 1, therefore, is also in this implicit type definition here. This inferred type is also string, so you can later extend it to contain more characters. Yeah, and there are no single quotes in Swift, right? So that's what I wanted to point out. Unlike C, for example, you don't have a single quote around individual characters. So even here, we are still using double quotes. All right, now checking whether a string is empty. If we define a string and we can call myString.isEmpty, we can ask for this property of myString and find out whether it is empty or not. Now, you could also compare it to the empty string, of course, right? But there's actually 3 reasons why you maybe not want to do this. First of all, this just reads better. This is something, if my string is empty, if I read this aloud, it literally sounds like I'm speaking a proper English sentence, right? So that's better than my string equals, quote, quote, something like that. The second reason is this is something that all collection types offer, not just string. String is a collection type. We'll see more of them in others. And for consistency, we usually ask if a collection, if something that is a collection type is empty, using this property. And then finally, it's also marginally faster. It's all the implementations of isEmpty in the collection types that we'll talk about are actually O of 1, so they're constant runtime. Whereas, if you compare it to the empty string, it could be slower. People have been poking around in this. Although I guess the biggest reason is this is also just how people write code, right? This is a Swift convention using this rather than comparing. Now, concatenation and interpolation. Concatenation is easy. You just, plus is overloaded to work with strings. You're used to this probably from other languages. We can also already here see this compound operator where you basically, say S4 plus equals, which basically means add this to S4 and assign it back to S4, right? So this expands this string here by one word at a time. Interpolation, string interpolation is a specific term that maybe you're not used to. So what it means is that this is the way that Swift lets you integrate the raw values of variables, constants, or expressions into a string, right? It basically does that using these parentheses around the expression and then a backslash in front of that. Right? When you write this, that basically says insert the value of a at this point as a string, and tie everything together into a complete string. All right. So next up, equality comparison. You can compare strings with the double equal comparison. And all this is, this lot of code is telling you is basically it's case sensitive. Okay, so if you want to compare things in a case sensitive way, one way to do that is to just ask for them to be turned into lowercase before you do the comparison. Right? This is what we do here. We turn Johnny Appleseed as the name into lowercase, and we do that comparing this to this, also lowercase, and of course those two are equivalent. Here you can see we're also not just using properties on strings, we're also using methods, right? So lowercase parentheses indicates that we're calling a method on strings. So strings appear to be quite a powerful data type. And as I said, they are a type of collection. There's lots of more useful functions available, like you can do things like has prefix so-and-so, or has suffix so-and-so, or contains this and this other string. If you want to see more about what you can do with strings, we're not going to throw lots of APIs here at you. Please take a look at the textbooks. The fundamentals textbook has a bit more examples and some lists of what's available in a nice tutorial style. Or you can, of course, always go to the language guide and read the corresponding section there. Now, that's strings. Next up, functions. Functions in Swift are defined using the func keyword, F-U-N-C. So the very general way to do this looks like this. And there's a couple things, again, it's syntactic sugar that you just need to be aware of. First of all, what might be unusual here is that the return type is specified with this arrow, right? So this right arrow that you kind of cobble together using a minus sign and a greater sign basically indicates that after that comes what the return type of the function is. Everything else is pretty much what you're used to here in writing this down. This is the simplest case. I have a function that doesn't take any parameters, that doesn't have a return type like display pi, and it just prints this out to the console. Right? So that's an easy way to write a function. Easy enough. By the way, this is at around page 169 in the fundamentals book, if you want to kind of like read along at home in there. If functions have one parameter, now this is something you need to pay attention to, because this is unusual about Swift. If you're an old school Mac or iOS programmer and you're used to Objective-C, this will not be surprising, but otherwise it might be. Swift requires you, usually, we'll get to the exceptions later, to actually put the name of a parameter into the call of a function. What do I mean by this? Well, here's a function called print triple, but it has a parameter called value that is of type int, and it just takes it times 3 and prints out the result. Now, this is not exciting, but what's exciting is this call, right? Look at this call. It says print triple, and not just 10, as you would be used to from Java or something like this, right? It actually says print triple value colon 10. So we actually need to name the parameter again when we call the function. You must say, huh? That's a lot of writing. Why would I do this? There's actually a couple of really good reasons why this makes sense. One reason is legibility. Once you end up with several parameters, this makes your code much more readable at those points where you are calling a function. Right? So as an example, here's a power function that prints out the power of a base and with an exponent. And it's just implemented in a very straightforward way. But what's interesting and what I want to point out, and that's why it's set in boldface here, I always try to highlight things in boldface that are most important to look at on the slide. You call this function with print power base to exponent 3. Now, if this had been Java, you would have said print power 2, 3. And 3 months later, are you going to remember whether base or exponent came first in your parameter list? You actually would have to go to the definition of the function to be sure what's happening there. Okay? And yeah, with the power function, the ordering is kind of obvious. But remember those calls for some kind of network package, message call, which have like 15 parameters or something, like a port and an IP address and a protocol and whatnot, some flags. Once you want to figure out, okay, which one is actually which here, it makes it really hard to read code. Not so in Swift, because you will actually see when you read the code that this is, print power with the base 2 and exponent 3. It's perfectly legible. This is what I say when, remember the 3 things of Swift, right? Fast, safe, and expressive. This is expressive in the sense that it makes it really easy to read the code. The code is expressive when you look at it. So, that's parameter names. Here's something else that comes on top of that you're also probably not used to from other languages, and it's argument labels. Don't confuse parameter names and argument labels. They are used in they're used at the same spots, and they're very related, but they're not the same. Argument labels can make function calls even more readable and meaningful. Function calls, right? The point where I call a function, not where it's defined. What does that mean? First of all, ignore the underscore for the moment here. Let's look at this function, say hello. Notice that we're not just saying say hello person colon string, another person colon string. That would be normal, right? That would be giving the parameter name. And then we would have to call this function by saying say hello person Miles, comma, person Riley. But we are not doing this. We're adding another thing here. We're adding an argument label in front of that. And what that does is that when you call the function, you can use the argument label. So what that means is you actually have to use the argument label. So when you call the function say hello, you don't tag the parameter with person and another person, but you tag them with the words to and the words and. What does that lead to? It leads to the call reading like this: say hello to Miles and Riley. That's an English sentence, right? That's really easy to read. So you can see, this is why I get excited about these things, because from a usability standpoint, this is cool. This is like a programming language actually trying to make things easier for the programmer and the person reading code, right? That's why I love this stuff. So here we have the example of calling this function. You're actually saying say hello to Miles and Riley. Well, you could say, why didn't we just call the parameter to and, right? Well, that would read weird inside the function, right? Imagine if this said print hello to and. It's like, that's not really good to read, right, inside the code. So you notice how semantically calling the function and actually defining the function are two different spots where you need different language. And that's what these parameter names and argument labels enable you to do, right? So we're calling it with the argument labels, but inside the function, you use the parameter names then to refer to these variables. All right? Now, you might say, sometimes I have a function like the print function, for example. Imagine the print function would ask you to every time label the argument of the print function with the word message. That would be kind of superfluous, but because, hey, what else are you going to do inside a print function, right? So obviously the argument is the message to be printed. So Swift does allow you to drop all this stuff. So you can actually say, well, I don't want the user of this function to I don't want to require them to use any label at all. Basically going back to Java style function calls, right? So look at this. This looks like Java, right? Say hello, Luke, Dave, or C or C++, whatever you want. We're not seeing any labels. Why? Because inside the function definition we use the underscore, which is a special argument label that says the user doesn't have to specify anything, right? They can just write down the parameter value. Now, use this sparingly and with good reason, right? Because when you use it, it tends to make your code shorter to write down here, but it may also make it more confusing, right? So only use this if it's 120% clear what that parameter could be, right? So usually you want to maybe use this only if you have something like, very obvious parameters that everybody understands clearly what they are. If you're not sure, don't drop the argument labels and the parameter names. It might sound like more stuff to write, but actually autocomplete is so good these days. It'll offer all these things to you. Just hit tab, pick the right function signature out of the list of proposed options, and you're hardly ever actually typing out any of these things. Usually you're just auto-expanding them and using the one that you want. And then it creates readable code. All right, so understand the difference between argument labels when calling things and actual parameter names inside the function. Next up, we have default parameter values. You can actually have a function where you say, well, normally I'm calling this with a parameter, but sometimes I want to maybe leave out the parameter and just use a default value. That's what this enables you to do. See, this function display here lets you put in a team name as a string, No argument label here, just a plain old parameter name, and a score. And the score actually here is specified as int, and it has equals 0 behind it. What that means is if I call this thing normally by providing both parameters, like down here, display team name wombat score 100, it'll output that, right? That's what the print line does here, just outputs the team name and the score. But if I leave out the second parameter and just call it with the first parameter provided, I'm missing one. So some languages, older languages would get a hiccup at that. Say like, oh, you're missing a parameter. Ooh. Here we can say, well, if you miss that, then I know you want me to use the default. So the compiler just basically uses 0 at that point, and that's what you get as an output, wombat 0. Now the attentive among you are going to say, wait a minute, isn't that kind of clashing with this leaving out argument labels stuff? So how does the thing know if I have a bunch of parameters that I provide inside an argument, inside a function call, which ones I'm leaving out and which one I'm referring to? So the tip is to avoid this confusion, because there can be situations where the compiler cannot make up its mind what you actually mean, is to put any arguments that have default values at the end of your function call. So they go all the way to the end of the parameter list that you have, and always add an argument label to them to just avoid confusion, right? So that helps you to avoid situations where things become ambiguous. If you want to see some examples, check out the fundamentals book on that. Next up, we got return values. If you want to return something, as I said, you do a little arrow and then the type of the return value, right? And here's a simple way to do that. You basically take these two numbers and you multiply them and return the result, right? It's an exciting multiplication function. How do you call this? Well, very simply, this is stuff that you know from Java, so I don't need to get into this. What's interesting, and this might be something that not always, that your languages that you know don't always support, is this one, right? Function multiply first number, second number, slash int, same thing here. And then comes something weird, because it's just an expression here, right? Anybody, who lives and breathes C compilers gets very nervous here, right? It's like, wait, this is not a statement, that's an expression. So we can do this because we only have a simple return value that we can directly compute, and we don't actually need to put the word return here as to make this a statement. So we can do this. And then that just makes writing these functions a little shorter. So with everybody refreshed and ready, we're going to dive into one of the data types that usually are kind of like the ugly little step sibling in a language like C, for example, and they're not really used for much, but in Swift they really take front and center stage, and that is structs. So if you define a struct in Swift, what you're actually doing is you're introducing a new type, right? Just like int, for example. And in fact, most of the basic Swift types that we've talked about here, string, but also even int or double, float exists too, by the way, or bool, are actually structs. So they are struct types. And what's most important to remember maybe about structs is two things. First of all, they are value types, meaning that when you copy a struct somewhere else, like a value of a struct into a new variable, that is actually copying, right? So if you copy and then change the stuff in that second variable, you're not going to change the first instance of that. Very different from what you're used to with classes and objects, right? Objects, it's this thing up in memory space, and your object variable is really just you're pointing to it, your instance variable, and if you have two pointing to the same object, one changes it, the other one sees that change. So structs are getting copied each time, which sounds expensive and inefficient at first, but it actually turns out to be a major performance boost, and Swift UI, which we'll talk about later, uses it excessively. So structs are value types, while classes are reference types. That's an important distinction to remember. And the second thing to remember about structs is that they are basically that they are a feature in Swift that you're supposed to be using as much as possible. So Swift tends to favor structs much more so than other languages. And you tend to use structs until you really need to use classes. Okay? But that's only possible because structs can do much more in Swift than they can do, for example, in C. Right? You're not able to normally add methods to a struct, right? That doesn't exist. That's something that only classes can do. That's what object orientation is about. Here, structs will also be able to do that. Here's a very simple example. So we're defining a struct called person. By the way, types like person or int generally get capitalized, right, in Swift, and variable names start with a lowercase letter. So person is a struct type, and it has only one property right now, which is the name, which is of type string. Right? So that's very easy, and this is what you would expect a struct to look like if you compare it to, for example, C-based languages. If you then want to create an actual instance of that struct, so if you actually want to create a value of that new data type that we've just defined, person, then you need to basically call an initializer. We'll talk about more about initializer in a second. And here we've got a variable name like first person. It's a constant actually, and we fill it with a value of a struct that is being created by calling an initializer and setting the name to Jasmine. And then if we want to access that part of the struct, again, that's very much like what you're used to from Java, etc. You just access it using dot notation. Right? First person dot name gets you access to the name inside the person struct. So this is not too crazy. Another convention maybe that I want to put up here is we said that we tend to use let for everything until we need to use a variable, right? So there's a bit of a difference here in structs. In structs, we tend to define the individual properties of a struct actually as variables. Why? Because if we want this thing to be immutable, like a constant, we just basically initiate it, instantiate it with a let keyword, right? So this means this whole struct first person is immutable. It cannot be changed. It's a constant value that can only be set once initially. So we don't need to do this with every single property. Okay. And that's actually, again, a pattern that you'll see in Swift. As long as you can get away with it, you should also make your struct variables constants, right? Let constants, until you really need them to be able to change later on. Make your code safer. Now, as I said, one thing that might be surprising about structs is that they can actually have methods, just like classes. So here's an example. We add a method to our person struct, which is called say hello. It's got no parameters, but it prints out the name. And yes, as you can see inside the method, you can actually access the property just as you would expect it to be possible. And we create the person here with this instance, and then we call this function. So that's not too exciting, but what you should notice is we are initializing it by giving a value to the member variable or property name here by adding that into here as a parameter. This is what we also did in the last slide, and so somewhere this assignment of this value Jasmine, the string Jasmine, to the name property has to happen, right? So where is that going on? That's actually happening inside the initializer. So whenever you create instances of structs, the same is true for classes, by the way, and you know this from Java, you need to initialize their properties, right? Their member variables. So how do you do this? Well, as we said earlier on, the built-in data types are also actually structs. And how do you initialize them? Well, there is an init, right, that you can call. This is the default initializer that's provided for every struct. And this basically sets them to a reasonable value, right? That's part of the implementation of that data type. But if you want to save yourself some writing, you can just write string in parentheses. So you don't need to actually write dot init and parentheses This is just a shorthand version of that, which you will see a lot. Right? This is the way that most people write this. They don't spell out the init explicitly here. Here's an example of providing, both the using both the initializer that sets the value to the default and an initializer that actually sets the count to a particular value. Right. So if I just define my struct like this, I haven't written any initializers. Right. This is all auto-generated by Swift at this point. Still, I get one initializer, which basically lets me just use the default value, just like I did here with string and bool. But I can also use a different initializer. It's another init method that also gets auto-generated by Swift for me. I don't need to write it, which basically lets me actually set that variable as a parameter. Right? So both of these initializers actually get created for me automatically. And this is possible because Swift is pretty good at generating your initializers for you. You can, however, also decide to do them yourself, right? If you want to. For example, let's say we have, we have a temperature struct, and it holds a value in Celsius. And you also sometimes need to, set that value in Fahrenheit. Now, you could ask people to do the conversion themselves, right? Outside the struct, but that's kind of inconvenient. So the struct maybe could know about how to do the conversion itself. So that would be nice, right? But if you do this inside the struct, then what happens is that you actually end up with two initializers, and that's fine. And notice how just changing the signature here. So this is one initializer that uses the Celsius. Setting the Celsius property here, and that works just fine, right? But I can also, because I've specified a second initializer here that has a different parameter name, so that's a completely different function signature, right? Init Fahrenheit double is a different signature from init Celsius double, because the parameter names are different. And so that means there is a second initializer now that I can also call by calling temperature with Fahrenheit and giving the value. And that basically also sets the same internal value. There's only one property here, but two initializers. And this one then basically sets it to the proper value after doing the conversion internally to the struct. By the way, by using this let boiling here means that I won't be able to change that temperature struct after I created it, right? So it's now set to the 100 degrees Celsius, which is the conversion from Fahrenheit, and after that this cannot no longer change. But we use for storing the boiling temperature if you don't plan on changing that. Now, when you do add even one custom initializer, you actually must define your own member-wise initializers and default initializers yourself. So that at that point, Swift basically stops auto-generating all this stuff for you, and you are bound to write your initializers. Right? So basically you can't really mix and match and say like create a couple for me and I'll throw in some others. It's all or nothing. Maybe it doesn't happen too often that you end up writing your custom initializers, but this is how you need to do it. Now, changing values in structs. First of all, you can do this by changing the property directly, of course. Right? So here's the same example. We've created these two, and now we add something. We say current temperature is a var, so I can change its values after I created it. Right? It's fine. I just say current temperature dot Celsius, which gives me access to that property. Set that to 20.0, and that's fine. That works. But if you try to do that with the boiling temperature, it wouldn't work, right? Because that that would be a let constant then. However, this is not what we are used to, right? This is not usually how you change values inside a class. What would you usually write to do this kind of stuff instead? Yeah? I think you already murmured it to your colleague. Exactly. You would write getters and setters, right? So why not do the same with structs? So this is what we would do, right? We'd say we'd have a function. Okay, we'd maybe call it set Celsius, right? Or change Celsius, doesn't matter. And you provide a new value. See, we're even being nice. We're using the argument label 2 here, right? So it's really easy to use. We would write set change Celsius to when we call it, and then we just set the value to the new value, right? That sounds like that should work, but it doesn't. The problem with this is that there's another safety feature here in Swift that by default your functions that are your methods that are part of your struct cannot actually change the properties of your struct. By default, they have read-only access. If you want them to be able to do that, you need to flag them especially to do that. This is another safety feature in Swift that keeps things from going bad, right? So by default, everybody's locked out. All the member functions are locked out, and only those that are marked with the mutating keyword are actually able to change things. This lets Swift not only keep your code safe, but also do a lot of optimizations behind the scenes when it knows about these things. And, let's be honest, if we wouldn't have to do this, we wouldn't bother putting a non-mutating keyword in front of all the ones that don't need this feature, right? This is more like forcing us to do this explicitly, this extra work, if we want access, write access to the member variables. Note that we still, even though we do this, we still need to also make current temperature a variable, right? If this was a let constant, we still wouldn't be able to do this, because that access is not possible if the current temperature is a let constant, because everything is basically a constant value. All right, but this works, right? This current temperature change Celsius to 23.0, because we've declared it as a variable and the function change Celsius is a mutating function. That's fine. So this gives us full access to that kind of stuff. Now, properties are nice, but sometimes we run into situations where we maybe don't want to store a property when it is actually something that we can compute on the spot. Right? We might say, well, isn't storing faster than computing? No. These days, it's not with modern computing architectures. Computation is actually much faster than putting stuff anywhere. You can do so many processor cycles before you've stored one thing in RAM even. So computing is often more efficient than doing this. Plus, if you compute a value, you don't need to worry about it going stale. Let me show you an example. Let's assume we want to actually have a temperature struct that contains Celsius and Fahrenheit values at the same time. Normally, if you went really old school, you would have a Celsius property and you would have a Fahrenheit property, and every time one or the other gets changed, you would have to make sure that both get updated, right? This is asking for problems, right? You're going to forget about this at one point in your methods inside the class, and then these things maybe drift out of sync. Or maybe you're actually accessing these things from outside by direct access to the property, and anywhere in the code this could happen. And how are you going to ever make sure that these two things stay in sync? Right? So we got drifting values in the two properties that are inconsistent, not good. What we can do instead is we can actually have a Kelvin property still, but it's actually not storing any values. It's just computing it whenever it's asked its current value. Okay? So the Fahrenheit one. So Celsius remains a regular property here, but Fahrenheit is actually a computed property. What does that look like? Well, it's Fahrenheit : double, and then comes a curly brace, which is kind of like, huh? After a property value. But that basically means that this value is not stored. It's computed using this expression every time somebody asks about it. So obviously, you can't set it, right? You can't change that value, but you can ask for it at any time. We've done the same here just for kicks with Kelvin values. So that's just another conversion. All of them using the same stored Celsius property. Yeah?
Would it be possible to leave out the return keyword?
Yeah, you could do that, absolutely. That's a good example of where you would do this, because then you literally see like the formula there without everything else. So this keeps the state consistent, right? We only have the Celsius value ever, and we always know that Fahrenheit and Kelvin remain correct. Now, another thing that you can do with properties is observe their change. And this is showing, it seems like an exotic feature, but once you get into writing code using these, and especially writing code that changes data structures around, etc., this becomes very useful. So let's say we've got a step counter here. It's got a variable of total steps. It's an integer. It's initialized to 0, and it also has something behind it. So it looks a bit like a computed property, but it's not. Instead, what's in there? It has two special sections, a will set and a did set section. And these sections actually will get executed before or after the value gets changed or set. Okay, so when you do this, it basically means if I actually create a step counter here and then set its total steps to 40, what happens is that it will actually output about to set total steps to 40, then it will do the actual setting, and then it will say added 40 steps, because both of these things, will set and did set, are defined. So, and we change the value, so that happens automatically. So that's a very useful feature if you need to actually observe the change of a value inside a struct. All right, I'm going to talk way less about classes. First of all, because you know classes from Java, and secondly, because they're pretty much the same in Swift as they behave as you would expect them to behave. And I'm mostly going to talk about when you use one or the other, structs or classes. So classes, above all, are reference types. Just to really nail that down, reference type means when I instantiate a class, I've got an object. It's on the heap usually somewhere in memory, and my variable, my instance variable, really contains a pointer to that object in the heap, right? So, and when I create a second variable and I set it to be equal to the first variable, then that just means the second variable also points to that same object on the heap. Now, if I modify things through one variable, I'm modifying the object on the heap, the one. If I then ask the other variable whether the thing has changed, yes, it has changed because it's pointing to the same object on the heap. That's not how structs work, right? Well, structs, if I assign a variable the value of a different variable, literally the setting, the whole struct at that point gets copied over to be the content of the new variable. And then if I change the old one, the new one doesn't care, right? They're two separate copies and typically stored on the stack and not on the heap. So let's get to classes. So classes are reference types, and a basic class works exactly how we'd expect it to. Here we've defined our person now as a class, not as a struct, and we can define properties, we can define initializers, we can have methods in there, and this all works as you would expect it to work. This shows how you add properties, how you also what you can see in this example here is how you override functions, right? So classes support inheritance, and that's one thing structs cannot do. So structs do not support subclassing. Okay, structs are just their thing, and if you need a subclass of something else, then you need to go with classes. So here we see the typical way of doing subclassing. Of course, you mentioned the superclass right here behind the name of your class, and then what we can see is if that person already existed, and we now this class, we add a subclass to it, we can add additional member variables, so additional properties to it. That's possible. We can also override existing functions, right? So say hello was defined here. We actually need to say override in Swift, right? To say I'm going to change that function. Similarly to how you say I'm going to change the property values. I'm a mutating function. You need to say I'm an override function. I'm changing things in the superclass. Again, helps you also when you read that code to be aware of these effects. And then we see an initializer here that, again, you know this from Java, uses, among other things, the super init at the end of its own initializer to initialize everything else that the superclass already provides. So we don't need to copy that initialization effort and introduce, two copies of the same init code into two different places, which we don't want. All right, so the point here is mostly to be aware that in Swift, you want to use structs rather than classes. There are three primary reasons, I think, that you will find when you do need to use classes. The first one, as I just explained, is you need inheritance, right? You need subclassing. Right? If that's something you want to do, you need to use classes. The second thing is when you have multiple variables that share a common reference to an object in memory, right? So if what I just explained with, pointing around here with my arms and hands, if that's what you want, then by all means, go for it. So oftentimes you have a situation in which you are, let's say, creating a person record in a database or something, and you want to make sure that various places of your code are going to modify this person record, and you need to access it from different points in your code, but you want to make sure that they all refer to that one same record that's stored there. Then you're probably looking at using a class and instantiating that on the heap. The third reason when you use a class is if you have to. So when you're using a framework, that just basically is providing a class to you, then you're using a class. So one example there would be, and we'll see this very quickly in UIKit, UI view is like the parent of pretty much all the things that become visible on screen in a user interface in UIKit. And so in order to create particular ones from these, you do what you do in Java, you subclass from UI view. Right? So there you are bound to work with that concept. We're going to go through just a few more small topics here in the Swift language that you should be aware of. And then we're going to take an initial peek at UIKit. First of all, collections. I already mentioned collections. Strings are a collection. Strings are a collection data type, and they're a collection of characters, right? And there are lots of other data types that are collections, but we just want to point out two very common ones that you will be familiar with from probably other languages. The first one is the array. So any collection is there to store related data, right? A bunch of things, behind each other in a related way. So what the array does, of course, is just storing values, right? So the collection array is defined in this way. This will be a names array of base type string, and each element then is a string. So easy enough. Dictionaries are also a collection type, and the dictionary here. Dictionaries probably from other languages, right? So they are basically just collections of key value pairs, right? So you've got a key, in this case, a string, and you've got a value, in this case, apparently an integer. As you can see here also, we're not actually specifying the base type. It just is derived from this initialization here that we're doing in the code. Now, important to realize, collections are value types. I know in Java, for example, string comparisons are like this finicky beast. I taught Introduction to Java a bunch of years ago, and this was always a thing we needed to discuss and some extra. Collections are value types. Strings mean by that also means they are value types. So we are copying stuff back and forth every time we assign this to a new variable. And be aware of this. But we had this discussion here during the break. The whole idea about structs is that they tend to be fairly lightweight constructs. There's no subclassing because of that. And so they are fast to create and destroy. That's the idea behind structs. But that means that if you use an array with lots of stuff in there and you assign that to a bunch of variables all the time, you are copying that entire array in its completeness each time. So just something to be aware of. Let's look at arrays a little more. How do you initialize them? Well, so arrays start at index 0, of course, right? Good old computer style. But how do you initialize them? This is the first way to do it. This is an empty array with base type int, right? Since we're not initializing it to anything except the empty array, we need to provide the base type. Otherwise, how is it supposed to know? We can also do it like this in a second way here, where we say, okay, it's an empty array, and we use the array, the generics initialization over the base type int. This notation you probably know from C++, for example. You may have seen that, or Java. And here's a third one, and that's the one that you actually, yeah, I guess that's the one that I tend to see most often. So you initialize it with this base type int in square brackets, and then just the the function call parentheses behind this. Right? So this is essentially calling the initializer to create an array of base type int. Here are some ways of initializing them with something a little bit more advanced. So, for example, you can create an array, initialize it by passing in 2 parameters. Here we didn't pass in any parameters, right? So it was empty. But we can say that it's supposed to be filled with the value 0 for 100 times. So that would make an array of size 100. All the values will be 0. Right? So that's an initializer. As you can see, the init obviously has some tricks up its sleeve. So it's worth looking at the documentation for the array data type to see what other things it can do for you, so you don't have to write your own, oh, let's put a 0 into each of these 100 places kind of things. Here's another one. Here I initialize a constant array, so I'm not supposed to be changing that. Sorry, not an array, a constant integer variable, which is my array square 0. So that basically just accesses the first object in the array. Very easy. I can use my array in square brackets 1 on the left-hand side of an assignment. Right? So this can be the target of an assignment, which not all languages let you do that, but modern ones tend to do this. So I can basically set it like this. Right? I don't need to go through calling some kind of function on the myArray struct to do this. I can actually just basically put this on the left-hand side of the equal sign. I can also append something. Here I would have to call a function of the myArray data type called append, and then add a value to the end of it. All right, enough about arrays. Again, if you want to see more details, more examples, you can check out the fundamentals book. And we're going to move to dictionaries. So dictionaries are maybe something that you're not quite so familiar with as with arrays, because arrays exist ever since C was invented. So dictionaries are collections of a key and a value as a pair, and lots of these pairs. Right? That's the idea. How do you specify them? Well, here we can say that we are actually telling them there is going to be string and int as the 2 data types that we use. Again, we can also use the generic initializer for this, or we can use this interesting notation that means empty dictionary. Right? It just has this colon in between to indicate that we're always talking about pairs of values. So each element of the dictionary is itself a pair of 2 things. Another way to create them is, again, using an example. Right? So here we've got the scores dictionary. It's a variable one. We can change it later. And we put in 3 values, right? 3 key value pairs, sorry. Richard, Luke, and Cheryl are the 3 keys, and 500, 400, 800 are the 3 values that go in there. We can then, and this is interesting, we can then go in and just kind of like we did with the array, we can use the name of the dictionary and the name of a key that exists in the dictionary and make that the left-hand side of an assignment, right? So we can set the value for key Oliver to 399. And since that key doesn't exist yet, that means we are actually adding it, right? So we're adding a new key Oliver and a value 399. So that's kind of like appending something to the dictionary. Here, we're getting the old value first and then updating it. So we're getting an old value by scores update value 104 key Richard. What does that do? Well, it calls the update value function, which goes in, changes the value 100 for the key Richard. But before doing that, the update value function actually returns the old value. That's kind of like a nice side effect of that function. And we can make use of that to hold on to the old value before we do the update. we can also turn dictionaries into arrays, right? So there are convenience functions that say, I can actually initialize an array by saying, please make an array out of all the keys in a dictionary. Right? So that basically pulls the dictionary apart and puts everything that was in the keys into one array. And then we can do the same thing with the values, for example, too. So that's another possibility that shows you that you can actually work with these things quite nicely. And then here's a final example. We'll talk about the if-let statement later on. But what you can see here is we're drawing out, the scores for a loop and trying to find if one exists. That's basically what this if-let statement says. Then we actually print out my score. So we'll look up the score for Luke, and if there is one, which is the case in this example, then we print it out. Okay, so dictionaries are a really useful thing to hold on to key value pairs. I mean, you've seen key value pairs everywhere, right? From storing, for example, preferences, or it's also being used a lot if you see it in JavaScript, on the web, etc. So it's a useful thing. Now, on to everybody's favorite, the for loop. It's almost embarrassing, but the for loop, I'm just going to talk about what's different here. First of all, no brackets around the condition needed for loops in Swift, right? So you don't, just like with the if statement, you don't need to put brackets around it here. And here we're actually using a for in loop. As you can see, this is actually a giving an index in a certain range. And so we're not saying from 1 to 5 in the increment of 1 or anything like that. You can run loops on all kinds of things. On ranges, arrays, letters, dictionaries, and they can even provide the current index if you use them with the enumerated method. But let me show you some examples. So here we've got the case. Oftentimes, you're introducing a loop variable, but you don't really need it, right? You just want to count up. So you can use the underscore to leave that variable unnamed, right? Just for clarity. I'm not going to use that index other than just making sure this thing happens 3 times. Here's an example of an array with 3 strings, and we can actually iterate over that array, right? For name in names. Remember how we talked about map, reduce, filter last time? How that's like a nice way to remove the necessity for loops completely. This is kind of halfway there, right? We are at least able to say we still have a for loop, but we can just say, just do this for everything in this array. We don't need to put up a variable and iterate over the array by index like you would have to do in C or something. We can just say, go over the array, do this with every element in there. But so for in, however, has been a part of modern languages for quite a while now. Here's another example. You can do this with a string too, because string is a collection. You can iterate over every element of a collection, and so that you can say for letter in ABCD, print out the letter, and it would go through each of these. Here's another example. If we use abcd.enumerated, that basically means that it brings out the index for each letter and returns that as a dictionary entry. So we now have actually the index and the letter, and as you can see, we can use this tuple of index and letter as the actual loop variable, if you want to call it that, right? So that's a pretty advanced way of using it, but it's a nice way of showing that we can pull out these things out of dictionary, out of a string, turn a string basically into key value pairs, if you like, index and letter, and that basically gives you a way to access these things in an elegant way. Finally, here's maybe a little bit more advanced example. We've got an array that has, sorry, not an array, a dictionary that has a unicycle, bike, car, and truck in there with different numbers of wheels. Okay, and again, we already have a dictionary to start with in this case with 4 entries, and so we now go in and also use a vehicle name, comma, wheel count, so a tuple of these 2 things as a loop variable, if you like. And in doing this over the vehicle array means that we can also access them in the same way. So it's very similar to what we saw up there, except now we're explicitly already providing a dictionary. I think the battery is dying on this guy, so maybe something to look at after the class. While. The basic while loop looks like this. You got your setting up a number of lives, for example, here, and while it's above 0, we still print something out, and then we reduce the number by 1, right? So that's very much like you would be what you would know. As you can see here, we basically have different ways of exiting these things. So while loops run, as long as the condition is met, obviously. So be careful. If nothing affects the condition, you could create endless loops, which I think you're aware of. How do you get out of them other than having the condition turn false at some point? Which this is kind of like illustrating this way, right? That this is really just a Boolean condition that we're doing. But if you want to get out of this in a different way, you could also use the break statement, right? So break statements get you out of loops. All right. Now this concludes what we're going to talk about in Swift for now. There are some advanced topics in Swift that we will continue to get into, like optionals, for example. But we want you guys to also start getting a feel for what UIKit looks like. And therefore, we'll do a first introduction here, not at depth yet, but it'll be enough for you to get a feel for what the toolkit offers and how you might be able to assemble your own user interface using it. And this is a very rough overview. If you are interested in more details about each of these, I do recommend taking a look at the Foundations book for each of these UI view classes that I'm going to talk about. So UIKit is what probably the most important part of your iOS app is provided by UIKit. It has several classes, of course, and the most important one, we already mentioned it earlier on, is UIView. And UIView is essentially the base class for everything that becomes visual in a user interface that's built with UIKit. Remember, UIKit is the one way to build interfaces. The other one is Swift UI, right? So that's the big design decision that you can make at the beginning of a project. Am I going with UIKit? Has been around for umpteenth years, right? Ever since macOS 10 came out, and even it was inherited from Next Step, so it's been around since the 90s in some form or other. But UIKit, was developed for the iPhone around 2009 or 2007, I guess. And so it's been around for a while. It's very robust, very stable, very mature. Lots of examples out there on the web, lots of frameworks, etc. But as you saw, haven't talked about it in detail yet, but for the last couple of years, we've seen Swift UI come up as the new kid on the block. It's a very different approach in designing your interface that is more declarative. I specify more like what the end result should look like, and I don't care so much about how the app gets to do what I want it to do. So it's a different approach. It's more declarative, maybe more modern in certain ways, but it's not quite as mature yet, and you don't have, by default at least, quite the same amount of detailed, pixel level control over how your interface looks exactly. So that's a bit of a difference between those two. Now, we're talking about UIKit now, and we're going to go talk about this at length because this is the most mature one that we can present you. So some examples of what UIView might have as subclasses are things that you know from other languages, like labels, which are just pieces of text that you put on the screen without any means of interacting with them. Or a button, right, that can be pushed on, or an image view that can display some kind of GIF or JPEG image, or scroll view, right? So something that basically just adds scrolling capabilities to an existing piece, like an image or a text field. Here are some examples on these subclasses. So you probably know all these from many applications, right? So standard user interface components that you've seen in other areas. Here's an example of a label. As you can see, background and stuff like this, and the border around it is usually a standard feature that you can set in Xcode, when you design your interface. By the way, all of these things you will typically be pulling onto your canvas to assemble your user interface using Interface Builder. Right? When you work with Xcode, Interface Builder is that part of Xcode that lets you assemble your UI graphically, kind of like a drawing app, but with some extra features that Renee talked about yesterday. So here's another example for a text view. So this just outputs a piece of text into a larger field, multi-line text, as opposed to labels, which are typically just single lines. Image view, scroll view adds these scroll bars, which we see less and less of these days because of the tendency to rely on people knowing that they can scroll. Not a big fan of that. I like to be able to see that the affordance of scrolling is there, but so is modern times. And here's the tab bar, which you know probably from the bottom of your smartphone, right? That lets you switch between different sections of your program. We talked about this earlier when we discussed application styles, right? In many application styles where you have more than one screen of stuff to show or to share, this is a good way of structuring your app further into sub-screens, if you want, that people can navigate between. A UI toolbar is also its own thing that you know this from lots of applications you've used on your iPhone. And here's the navigation bar. Navigation becomes a major thing, right? Navigation is always going to be part of your interface because we can only show one screen at a time, right? So the navigation bar is usually always set in your standard productivity apps to go into a detailed view, back out again into another detailed view, having these kinds of interactions. And here is an example of a table view. That's also going to become your best friend. Table views are used a lot to display. You might think about tables just as something that you need to show when you're rendering like a number spreadsheet or something. But table views are used for everything that needs to be repeated down the screen, for example. So this one here, this setting here of which sound to play when in the system settings on your iPhone is using a table view to display all these different options here. Each line is a cell in this table view. Here are some things that actually are all summarized as controls. So a button, of course, is a control. The slider, the UI text field, which is one that you can also edit text in if you want to. The segmented control is one that comes up a lot when you need to switch between a few different options. It's kind of like the smaller version of the tab bar. And here we have the date picker. The date picker is interesting because it actually is it has this nice spinning effect, right, to set a time and stuff like this. But it actually isn't very effective from a performance point of view when you want to enter something quickly. And there's now alternatives to this spinning wheel in the iOS interface that look different, that let you set things more like with a little keypad. And here, of course, the UI switch. The UI switch is interesting because it actually usually resembles what's the equivalent of a UI switch in a desktop. How would you do a user interface on a desktop that you do with a UI switch here? Yeah.
A checkbox.
A checkbox. Yeah. Okay. So yes or no, right? So you'd have like sign me up for all your email, right? Yes or no. You make the checkbox. And here we use UI switches, and UI switches are a little trickier for people to understand than the checkbox, because oftentimes it's not perfectly clear whether which of these two states represents which logical state. Especially once you have like dark mode and an inversion of your screen, some of these logos get a little confusing to figure out exactly is this on or off right now. There are ways to fix that, but it's not something that UIKit offers by default. Now, how do you actually get into interacting with all this stuff? Well, one way to do that is to use gesture recognizers. Gesture recognizers are available to you when you build your iOS app inside Interface Builder. So basic touch gestures are basically things that you don't need to worry about. You don't need to figure out how do I differentiate, between that swipe and that drag that we talked about last time. You can just bring these gesture recognizers in actually using Interface Builder. You can also add them using code if that's more your thing. So really something that you don't need to need to do yourself either way. And here's some examples: tapping, pinching, rotating, swiping, panning. Screen edge pen gesture recognizes it, something that starts near the edge. A long press recognizer, custom gesture recognizes that you can build yourself. So you can also implement your own if you want to, but shouldn't be necessary normally. If you do need to do your own custom touch input, maybe you've got a complicated game that needs very special input that you don't want to, that you cannot use the standard recognizers for, then like you're tracking live data on multiple fingers and it sets something in your game or something, then you can do this with these three functions. Touches began, touches moved, and touches ended. Each of these tells you when a new touch was added or changed its position or was lifted off. And just think about this for a second. This is much more complicated than writing desktop apps. Right? Desktop apps, good old world of there's a mouse and it has a position, and when somebody clicks, I know what position they're clicking at, and there's only like clicked or not clicked. Maybe there's a hover state and I'm done. Right? Now you've got multiple fingers coming in, starting a touch. Then a second finger comes in, starts a touch. Then maybe the first one lifts off before the second one lifts off, or maybe the second one lifts off before the first. All of these things can mean different stuff, right? So handling basic user input is much more complex in writing mobile apps than handling user input using a mouse on the desktop, because the mouse or the touchpad to a certain degree are simpler devices. Touchpads, yeah, they tend to recognize multi-touch too, so you're roughly in the same complexity as on a smartphone, but the mouse is so much easier to handle. There's more about this, by the way, in DIS2, where we talk about how this event handling works. If you're interested, that's a class in the summer. Now, last slide before we get to the summary here. How does Model View Controller work in UIKit? Maybe as a mental sneak preview here, SwiftUI works differently, by the way. We're talking about UIKit here. So what happens in Apple's way of using MVC, which I'm assuming you guys are all familiar with, using UIKit, is that you still have your model view controller set up in these three different ways. If you're not familiar, again, check out the fundamentals. The model classes are typically the things that have persistent storage, like things like core data support this very well. And they talk to the controller. They notify it about changes, and the controller passes on changes that result from user actions to the model to update itself. So if somebody increases a number by tapping on a slider on a button, then that increase gets passed to the model, and the model, if it changes a value by itself because some simulation says, I don't know, time has run out or something, will notify the controller. And the controller in itself will update the view, which is defined in a storyboard, and the view will pass any user actions like input, to the controller. So as you can see, the setup is a little different from your standard MVC paradigm in that the controller actually kind of sits really at the center of everything. Right? It's the thing that ties view and model together. So you will see the word view controller a lot when you're writing UIKit code, because these view controllers is usually every view has usually its own view controller that it talks to and that it passes events onto, and that manages then what needs to happen to these events and how these end up into your model. SwiftUI does not use it this way. It's more declarative, as I said. UIKit was designed with this model view controller paradigm in mind. Although an MVVM approach, if that's your thing, model view, view model, is also possible. Now, let's wrap up. We've talked about strings today. We've talked about functions. So you now have an idea of how these work. We have introduced classes and, most importantly, structs, which are a thing that is quite unique about Swift. And we've talked about a bunch of collections, and strings, arrays, dictionaries are all examples of those. You've gotten a little bit of an idea of how UIKit works and what kind of parts you get to expect when you assemble your first user interfaces. Next week we'll talk about the dreaded optionals, and we'll talk about things like the guard statement and inspection. And we will, on the UIKit side, we will get into segues and navigation controllers to start putting together multiple views of an interface into a coherent UI. That's it. I'm wrapping up. Thanks everybody for listening, and see you again next week.
This content was provided by RWTH Aachen University.